This Google quantum computer that claims this supremacy, they call it, using techniques that my group developed. These experiments have been debunked.
This is Frank Verstraete and Celine Broeckaert, the authors of Why Nobody Understands Quantum Physics.
I am not a scientist, but we are both very creative. I play with words, and he has also to juggle with equations.
The professor of quantum physics at Cambridge University. He's a globally acclaimed theoretical physicist, the winner of the Lieben Prize, amongst other incredible achievements.
This blackboard, that is the center of the universe in my office. People would not have understood quantum physics. They would never have been able to come up with it. Everything is quantum. I've been working in this my whole life. Particle is there or not. How can it be in a superposition of being there and there and there at the same time? Our brains are not wired to understand this.
Sometimes you just have to accept it is what it is.
It was an absolute privilege to sit down with both of them and trying to get a practical understanding of exactly how everything around us works.
For me, the best news that has happened this year is the fact that the new ChatGPT is not much better than the previous one. Might be that we're already reaching some kind of a plateau.
If you could pull those 10,000 physicists together, what would you focus their attention on answering?
That's very, very good.
Frank, Celine, lovely to meet you both.
Hi.
Thank you for taking the time out. And today I've been fascinated to sit down with you both, especially since getting my hand on your new book, which is incredible. Before we go into the book, which is, Why Nobody Understands Quantum Physics, maybe you could just explain a little about who you guys are exactly.
So my name is Frank Verstraete. I'm a professor of quantum physics at Cambridge University, and I have been working on quantum physics for my whole professional life.
Amazing.
And I'm Celine Broeckaert. I am not a scientist, but I'm an author, an impact producer, a theater maker, and I happen to be Frank's wife.
Amazing. And so you guys have co-authored this incredible book.
Mm-hmm.
Amazing. How was it?
Quite a journey. Yes, but it was our little project. And thing is, I would never have written it without Frank, and Frank would never have written it without me, and that makes it really so special.
Yeah, it was very interesting for me because I'm working on very specific problems, but then to kind of open up your eyes a bit and say, why is what you're doing interesting for the bigger public? I had never really thought about this, and I was forced to think about these questions when writing the book, and this was very actually relevant also for me.
I really appreciate you guys coming to spend time with us today, and today you're going to be talking to someone who's kind of pretty Neanderthal in the physics arena, but incredibly passionate.
That's our target audience, actually. I'm also the target. I'm also we are from the same race.
The reason you're here is because of this title and and your credibility, obviously. But we were really, really excited to try and get to the bottom of understanding this quantum physics, because it plays, in my opinion, and hopefully you can help me better understand it today, a pivotal role in some of the transformational technologies that we're exploring today and the journey we're on. Mm-hmm. If you could help us understand, what is quantum physics and why is it important?
So first of all, I wanted to comment on this fact that indeed physics is something that appeals to some people, because I think an extremely important fact of the exact sciences is that it's not something personal. It's not something subjective. It's something objective. It's something that you can understand and you can reproduce it, and it's there forever. There's no alternative truths. There's just one truth. And that is why physics is a different topic. It's a different subject in school that appeals to a specific type of people. There's something very universal behind it. And that's indeed what physics is about, trying to distill the essence of how the material world works. Yes. So it's a very materialistic thing. Physics is about matter. It's about how things bind, why things are as they are. But it's something that is very tangible and reproducible. There used to be lots of physics. Started, probably the greatest physicist ever was Newton. He basically invented the way modern physics is done. Okay, that there's some theoretical model, and then you can test it. And if the experimental test satisfies the rules, then you accept this and so forth. And then there's some refinements you have to make. Maybe Einstein came along and said, okay, Newton is not exactly right. You have to kind of make some adjustments. This is relativity theory, but still there was something that was completely missing in physics up to 100 years ago, and that was the understanding of why is matter does matter exist? What are the forces that basically hold the world together? What is it that gives rise to fluids and solids? And what are the forces that are at work there? And it's only 100 years ago that this was figured out. Exactly 100 years ago, actually, there was two very smart people, Shrodinger and Heisenberg, who wrote down the equations of quantum physics. This happened in 1925, and suddenly everything fell in place. So quantum physics was like the enlightenment of physics. Before quantum physics, we did not understand anything of matter. We could not understand why things binded, why matter was hard, what was it that gave color to things. And suddenly there's this quantum physics and everything becomes clear. So it was like, in some sense, the biggest revolution ever in physics. And but there's a big paradox, because the equations that clarify that or explain this or allow you to predict things and to confirm things by doing experiments are very strange. The theory of quantum physics is something that is very unintuitive. It's something that, because something is both a particle and a wave, particles can be here and there at the same time. So these are all things that we don't have any intuition about.
When you say that, you don't have any intuition over it, do you mean that it's not logical? Is that, or is the logic more complex?
Indeed, there's a different logic. It is very logical, because at the end there's a mathematical framework for it. Yes. And so because there's a mathematical framework that describes what is going on, of course this is logical, but it's not, it goes against the intuition that we have about things. We don't feel that you can go through two doors at the same time.
Yes.
But quantum particles can do that. Yeah. And the magic is that you need these very strange properties for matter to exist.
Yep.
If this would not be the case. So basically what quantum physics tells you is that there's a smaller scale. Okay, so if you kind of zoom in, at some point you cannot zoom in further. Okay. You're stuck. And that's that scale. There's this quantum laws that come into action that are, where particles can be at different places at the same time and so forth. But that's exactly needed to basically hold everything together. If this would not be the case, everything would collapse immediately. So this smaller scale is actually something that is also very visible on the scale that we live in. Okay, like the matter scale is all about, but you needed a smaller scale to do this. And to get this smaller scale, the fact that you cannot zoom in, the laws have to change. So you need these very complex laws for matter to exist.
Right. So breaking that down, just simplifying that even more. If you were to just say we've got traditional physics, we've got quantum physics, is the difference materially between those the level that you are getting to, atoms or particles? It's a more detailed breakdown of the same principles.
Indeed. So there's no contradiction between quantum and classical physics. It just happens if you put many particles together that these big objects start behaving like they're much easier to describe.
Right.
And that's exactly what Newton figured out, what the laws are to describe big systems. But then you get to smaller things, and then, okay, the particles and waves, it all becomes a very big soup, and it's very, very complicated. But nevertheless, there is kind of a continuous way of going from one to the other one. And the first person to see a glimpse of this was actually a very interesting French character, and his name is Louis de Broglie. It was a prince, actually an actual prince, that he had worked in the First World War. He had worked on the Eiffel Tower with communication. So he was a very big expert in everything that had to do with waves. And he just out of nothing said, "Oh, probably every particle is also a wave." And that turned out to be the key in unlocking everything. And what he introduced is something that is called the de Broglie wavelength. Okay, so to every object you can associate a wavelength. And the heavier something is, the smaller the wavelength.
Yeah.
Okay, so if something is very light, has a very big wavelength. If something is very heavy, it has a very small wavelength. And when is quantum mechanics? When do you need quantum mechanics to describe a system? That means that you need to describe quantum systems. You have to describe them quantum mechanically if the different particles have overlapping waves.
Right.
Okay, so if the wavelengths are very small, you don't need quantum mechanics because these waves don't overlap. Because like my wavelength is something like 40 zeros and then a 1 small. So it's like incredibly small, but the wavelength of an electron is actually very large.
Right.
The wavelength of a photon that doesn't weigh anything is huge. That's why photons or light is purely quantum mechanical in some sense. And that's the key in understanding when do you need quantum or when do you need classical to describe something. It has to do with what is the distance between the particles and what is their de Broglie wavelengths.
What you're talking about there is the quantum is introduced based on the distance and the relationship between particles. And if there's an overlap in the wavelength of them, it then introduces quantum and quantum mechanics.
Exactly, because if you have overlapping waves,
Yep.
you get interference effects. That's what you see in the waves, no? In
Right.
the bond. Like if you throw a stone, you see this interference effects. That's going on. So if you have two waves that overlap, then you have interference effects, and that is the mystery. That's basically the defining property of quantum mechanics, that everything, these waves, you need the wave functions. So what is fascinating is that the mathematics to describe like one quantum particle is the same as the mathematics for describing many, many classical particles.
Right.
Because many classical particles also can form waves, but you need the same equations, but to describe one particle. And then you put several particles together, and of course things become much more complicated. And these are basically this Schrodinger equation. That's the equation that was discovered exactly 100 years ago.
You mentioned something there which is about the relationship that many traditional or normal particles can have the same effect as one quantum particle. Is that right?
Somewhere, yes, yeah, that one particle is a wave. It's both a wave and a particle. But of course, the interpretation of this is completely different.
Right.
If you have a wave, it's a classical wave is really because you have many particles, and you can say, okay, this is the way. The wave function or the wave of a particle is something very esoteric. It's not that this particle is a wave. It's just that this particle is at many places at the same time, but it has to do with probabilities. So the wave function is something that encodes the probability that if you would do a measurement, what is the probability that I would find a particle there?
Right.
So then, as you see, it already becomes extremely strange. Now, this is something that we don't have. Yeah, a particle is there or not. How can it be in a superposition of being there and there and there at the same time?
Yes.
We don't. Our brains are not wired to understand this, but that's the reality. It turns out that this is how quantum mechanics works.
You must have a field day asking him questions
No,
about
go
all
ahead.
the different
It's
dynamics.
lovely
of
to
it.
see you so curious. That's the reason why we wrote this book, to make you think about the
I
material.
mean, it's
and
the perfect title. Why
Well,
nobody
yes,
understands
yeah,
it.
yeah.
I keep digging into some of the same stuff here, but explain that part. Get that last part again. Then, so what you're talking about is the complexity for us to get our heads around quantum is the fact that these particles can have different states. Is that what you were saying?
Yeah, okay. They can have different.
locations?
They can be in different, let's say, places at the same time.
Right.
Maybe let me take actually a huge jump
That's fine. Yeah. Go
in
for
the
it. future.
future, like what is going on in research now.
Yep.
This is precisely how quantum computers are being envisioned now. That something can both be in a superposition of the bit 0 and the bit 1. So,
Yes.
Okay, so this is effectively the same principle. Okay, so particle can be in many places. I have like a double well, and say if the particle is in the left-hand side, it's the 0 state. If it's in the right-hand well, it's in the 1 state. But now with quantum, I can be in both at the same time.
Yes.
And that is exactly kind of the mystery of the magic of these quantum computers, that you can start doing things in parallel, because you have this object, these quantum particles can be in two different wells at the same time.
I think this is really interesting, and my reason for getting into this and really trying to get into the basics of it is because it's foundational to a couple of technologies which are becoming more and more prevalent in our everyday lives, right? And quantum computing and quantum communication, a lot being spoken around encryption and the kind of practical applications of these technologies. I mean, it's in the news on a daily, almost daily, weekly basis with innovation, whether it's China or if it's IBM, Google. There's just such tremendous rate of progression. This can have an absolutely profound impact on society. My understanding of quantum computing is absolutely the state, like you've just said. Traditionally, a computer can have a 0 or a 1 state. In quantum, very simply, it can have both. Correct?
Well, it's more than both. It can be a little bit one and the other, but everything in between. And it's not just a probability. It turns out that you say it's a 0 plus some constant times 1, and the sign of that constant also matters. So there's something, the phase, it turns out to be a complex number. It's like there's much more complexity to it. So it's something that still nobody really understands.
Right.
I've been working on this my whole life, and I start being able to work with this, and you get an intuition about it because it works. But to really explain it, what does that mean? What is a superposition? I'm still not able to do this.
Yes.
Okay. Besides, I understand that this from the mathematics point of view, it's very clear, and it is exactly that principle that is needed to explain basically how the world works. Okay, without quantum mechanics, as I said already, we didn't understand anything about the world. By the way, I think this is also something that we should talk about before we talk about the new technologies, is that all the old technologies in information technologies, like the transistor, the laser, all these things are completely 100% based on quantum physics. So if people would not have understood quantum physics, they would never have been able to come up with a transistor.
Right.
It would have been completely impossible. So a transistor is a purely quantum mechanical object, but at the end, you don't make use of the quantum mechanics. So you use the quantum mechanics to build a transistor, but then you put that particle in the 0 or the 1 state, and that's it. But the way to build it, underlying this technology, is the band structure of electrons. You need to understand basically how electrons work in a material and to engineer a material, and this is a purely quantum mechanical process. Same thing for the laser. Actually, the laser, which is, of course, our world is called, all of information technology is based on the fact that we communicate with lasers. This is something that was, there's also fantastic history. It was something that was discovered by Einstein. In 1917. He was working on general relativity, and he got stuck, and he said, one day he said, let me think about light at some point. And then in one day or two, he discovered the fact that a laser should be possible to create. And then it took 50 years for people to actually put his theory in practice.
Yes.
So these time scales are also very interesting. 50 years. Then people started making the first lasers. And nowadays, of course, there's lasers everywhere. And this is also purely quantum mechanical process. Has to do with symmetries, with the indistinguishability of photons or of bosons in some sense. And this is somehow the old technology.
Was that Einstein's main contribution to quantum?
No. His main contribution to quantum actually is much earlier.
Right.
Is in 1905. So the whole history of quantum started actually in 1900 with Max Planck. So Max Planck was a very famous German professor, and he worked on thermodynamics and on trying to understand how light, let's say he wanted to predict how the energy of light is related to the temperature and many things in a black box. And there was some mystery. The experiments did not fit at all the theory. And he realized that to kind of make a theory that fitted the experiments, out of his head, he pulled somehow a constant. This is now the very famous Planck constant on which all of quantum mechanics is built. And he said, if we assume that there's a smaller scale of energy, then suddenly we can kind of match experiments with theory. Okay, but it was so weird that you had to make this assumption. People thought this is just a mathematical trick. There's nothing to it. But then Einstein came in 1905 and said, no, this is not just a mathematical trick. It's something very physical. He really kind of realized that this Planck's constant meant that photons, like the way we kind of understand photons or light, that they are made out of particles. And that this smaller scale, this h of Planck, had to do with the unit of how many photons are there in a wave packet. Right. So he realized that this is something very physical. It means that photons or light consist out of particles, and these are called photons. And that was, he did this using the photoelectric effect, but that's actually the main contribution to quantum. And this was the first time that quantum was taken seriously. And that's actually for that thought experiment or that idea, he got the Nobel Prize. He didn't get the Nobel Prize for relativity theory, actually for that thing. And he said from himself that this was probably the most original idea that he ever had.
From that point, you say that we got to a place where, I think it's in the 50s or 60s with transistor, isn't it? We end up becoming an absolute kind of another transformational point in our technological roadmap, the evolution of technology. And so that again came from the principles of understanding quantum.
Yes. So the people that discovered the transistor was the main person. That was Bardeen. Bardeen was a very famous quantum physicist. He was a condensed matter physicist. He understood like nobody else what happens when you put many particles together and how to solve this quantum mechanically. And I said, okay, now I have to engineer a material such that the band structure of these electrons is of that kind, and that's how they came to semiconductors and doping the semiconductors. So it's a pure theory-driven approach. It would never have been discovered without quantum.
Let's take a step back there, actually. And I did say we might end up going in different ways.
No,
here, right?
That's also how physics works. It's like it's not linear.
So help me understand what are the main milestones in the journey of quantum physics?
Yeah, so there's clearly something like 5 or 6 absolutely defining moments in the history of quantum mechanics. And I think the first one is 1900 with Max Planck. He introduced something that is called the Planck constant, and it was a mathematical trick. He used this mathematical trick to explain some experiment that he could not explain without having some constant there. He had to assume that there was a smallest energy somewhere in a system, and by this he could explain the black body radiation, because there was a violation of the theory and the experiments didn't match. And he said, if I kind of put some constant in my formulas, then suddenly everything works. But people didn't realize at that point it was just a mathematical trick, and nobody took it seriously. Until Einstein came along in 1905, 5 years later. He said, no, this constant is not just some mathematical trick, it's something very, very physical. What Planck discovered, he realized, is that photons are particles. That there's something that light consists out of photons, and that these photons are effectively particles. That a light wave is quantized. That a light wave can only have a certain amplitude, can have amplitude 1, 2, 3, and so further, but nothing in between. That's actually where the name quantum is coming from, because it's like a quantum is like a unit. Okay, it's the smallest unit, and that's the amplitude of the wave, so the height of the wave cannot be anything. Has to be quantized.
Right.
And that was the main insight of Einstein, and this is the real start of somehow taking quantum seriously. He said, photons are particles. Okay, and this is something was very revolutionary, because everybody was, since Jung, the experiments of Jung actually here done in London, they were convinced that light, of course, consists out of waves, because you have interference effects and so further. Yes. And that started basically the paradoxes. But then a few years later, Rutherford is doing experiments with atoms and sees that atoms consist out of a tiny, tiny nucleus, and that electrons are effectively flying around that nucleus in a much bigger orbit, and there's something like very strange. Nobody understands what is going on. And then Niels Bohr comes along, which was a student of Rutherford. At that time, they were still in Manchester, and he kind of comes with a model. He says, actually, these electrons live on some orbits. An electron is something that can only traverse some orbits around that nucleus, and the orbits are quantized. They can only kind of be on that orbit of another orbit with specific energies. Okay, but again, something like a mathematical trick. Yep. And then exactly the same thing as before, but Einstein versus Planck. Now, what happens is almost like something like 10 or 15 years later, in 1924, Louis de Broglie, the prince, comes along and says, but actually what you discovered, Bohr, is not just some mathematical trick. What you tell is that every particle is also a wave. Okay, so it's basically the opposite of the first study. Okay, so you remember Einstein said photons or like light consists out of particles, but now de Broglie says the opposite. Actually, every particle consists out of a wave.
Right.
And that was then somehow this opened up, but suddenly everybody realized, but okay, so it means that both particles, waves, particles, we need a wave equation. We need an equation. If you have something that describes waves, we need an equation that describes these waves.
Right.
And that is actually the biggest revolution happened in 1925. Independently from Erwin Schrodinger and Werner Heisenberg, they discovered quantum mechanics. They discovered the equations that govern these waves.
Right.
Okay, and that is a very abstract set of equations that basically explains everything. Okay, suddenly all kind of doors open, and suddenly everything could be explained. So this was like the biggest revolution in physics ever. So suddenly after these equations, people started using this and started realizing, yes, everything is quantum. I can understand the periodic table with it. I can understand matter with it. I can understand chemistry with it. I can understand nuclear energy with it. So everything basically opened after that realization of quantum mechanics. And then basically these equations are there. And in the last 100 years, the big research program has been driven by trying to understand these equations. So these equations are actually very hard to solve.
Yes.
And all the biggest breakthroughs in quantum physics since 100 years are trying to find new ways of solving or approximating these equations because they are very, very hard. And that is still kind of the open problem. So we have the equations, we cannot really solve them, but also we don't really understand what they mean. Okay, there's still some kind of a philosophical problem with interpretation. What do these equations that actually govern everything, by which we can explain everything, by which we can make technologies? Because like I said, the transistor is based on it. Without the understanding of these equations, we would not have the transistor, we would not have a laser, we would not have NMR, we would not have many, many things. But nevertheless, what do these actually mean? And that is still completely open.
The question I've got, right, is that you've said this a few times where you've said that we've got equations that explain these phenomena or these relationships, okay, but we don't understand them. What does that mean?
So for this, of course, you first have to define what it means to understand something.
Yes.
Many people, I think everybody has a slightly different definition of what it means to understand something. Understanding something is that you can relate it to many other things. Okay, so for me, understanding something is like you can put it in a bigger picture. You can say, okay, this is a logical consequence of this, and I understand this, and this fits this intuition. So you can relate something to many other things. And
give me a practical understanding. Try and put it into an everyday example of how you might have the equation for it, but you might not understand it.
Okay, let's first try to find an equation that we understand. Okay, look at the equations of motion of Newton about an apple that falls from a tree.
Yep.
Okay, that's something that we can see. We understand that there is some motion and that these formulas do this, and you can fit this, and you can see it, and okay, yes, it fits. It's easy to understand, okay, because you can actually view, you can look at it, you can do it yourself, you can do the measurement, you can do this.
Yes.
Okay, but in a quantum setting, these equations have a very different meaning than the equation of the trajectory of an apple, because these equations tell you that this particle is at different points in space at the same time, but you never see a particle at different points in the same time. If you look at it, you only see it in one place. Yes. If you do a measurement, you see the particle there, not in a superposition. Okay, so it's something you cannot see. You get something that you have to assume that this is true, and you see these equations, you solve them, and then you do measurements, and you see that everything you measure is in accordance with these formulas.
Yes.
But there's something missing there. There's a level missing. You cannot see this wave function. This wave is not a wave. It's not that you see some ripple in space somewhere. Yep. You cannot, because the meaning of this ripple in space, this wave function, is something about information. It turns out, and that's the magic, and that's really the new way of thinking about quantum mechanics, that these wave functions basically are about information about the system. Okay, so the wave function tells you what is the probability that I will see a particle if I would measure it. Okay, but what is the probability? That means it's about information that if I do a measurement, this is what I will see. So there's a very strong link between information theory and actually quantum physics. Right. And that makes it so difficult. Okay, so it's something very abstract. It's something that you cannot touch, you cannot see the wave, but it's the only way in which we can explain what is going on. Okay, what it means now to understand things is, of course, to be able to use them, to predict new things with it, to feel things. And of course, by working with this, at some point you get an intuition. And that's how Bardeen was able to solve, basically, to discover a material by which he could make a transistor.
Yes.
Because you start getting some intuition, some feeling about this. But still, there's a big tension there. And every physicist in the world that has been working with quantum physics has this strange feeling that, okay, mathematically everything fits, and I can use this, but there's something lacking. And then there's basically two possible attitudes towards this solution, and I think the most prevalent one, and that's certainly I think also the most useful one, is to shut up and calculate. That's actually a literary quote from David Mermin. Mermin is a famous person who said this, but actually was also very interested in foundations. Or you can start looking, okay, let's try to do more, kind of look more at the philosophical aspects of this and try to understand this. But it turns out that second attitude has never kind of led to any progress. Okay, so the attitude of physicists, and certainly is more the engineering attitude. We have this, let's not bother too much about interpretation. Let's just use them and try to kind of make things with it. Said in a very nice way by Wheeler. Wheeler was the thesis advisor of Feynman, that some people, probably some listeners will kind of know. Feynman was one of the absolute genius. And he said that you have it from bit. Okay, so that you only have something because of the information it contains. That actually the information is the basic of everything. So nobody really understands that quote, but everybody uses it because it exemplifies this. There is something there. There is something that is about information, and these equations are not describing, in some sense, the reality. They are describing the information that we need to have to describe reality. Okay, so, and that is quantum mechanics. So it's on a meta level. There's something going on there.
And that information effectively would be used to describe what the properties are of that matter.
Exactly.
In a very simple form.
Yes, no, that's exactly what it is. So using that wave function, you can deduce all the information. You can deduce the resistivity, or you can predict, I will be able to make a superconducting material, something that has no resistance. Or I will be able to make, if you kind of cool this material down, this will become a magnet. These are pure quantum mechanical phenomena that are properties of this wave function. So you look at this wave function, look what it predicts, and then these are somehow the properties of matter.
And the reason this is so important, and the reason there's so much passion and people like yourself which are really pioneering and committing their lives to understanding this, is that foundationally, the more we understand about this, fundamentally it comes back to really the biggest question is around our existence, how we got here and actually where we're going. Because understanding, looking back and looking forward accurately, my understanding is dependent on our better understanding of this particular topic. Am I right in saying that?
Yes. Well, I'm not completely out of it myself. From my point of view, physics is the most materialistic thing that you can have in the world. Okay? It's purely about matter. It's not about feelings. It's not about interpretation. It's very objective.
Yes.
Okay. And there's no alternative realities or truths. No, it is what it is.
And I love that, by the way. And let me tell you what one of the things which I love from Elon. And it's amazing. I think this is a brilliant business application, which is, I don't know if you've seen him, but he often says, if there's no part of physics that says it can't be done, then we must find a way to do it, which I think is an amazing mindset for many people, actually. And whether you're an Elon fan is irrelevant, but I just think it's a great point of view because often we have such limiting beliefs.
No, but okay, but you don't have to take it too far. So people have indeed taken this mindset when building a fusion reactor. Okay, and they have promised to build this already, like I think 70 or 80 years, and it's always 10 or 20 years in the future. Okay, so it's not because it's possible and technological possible that we have enough resources on the world to actually do it.
Right.
Okay, so you have to. I completely agree with the spirit of
yes.
But it might be that there's practical kind of limitations. So one of the amazing things is, like, of course, one of the biggest success stories of quantum is of course building the atomic bomb. Okay, which is one of these strange things. No, is it a success or is it a good or a bad thing? But nevertheless, it's absolutely amazing. You put all these quantum physicists together for 2 years, and they were able to make this. Yes. This is absolutely stunning that in such a short time period, when you kind of put all the energy of something like 10,000 physicists together, and you actually have a product like that, that is absolutely mind-boggling.
If you could pull those 10,000 physicists together today, what would you focus their attention on answering?
That's very, very good. Well, first of all, I think there's much bigger problems in the world right now than physics. Okay, we are really kind of living in completely transformative times, and I have the feeling that the world is not going in the right direction. So I would rather kind of ask these people, think about how we can change the course of the world again in a good direction, in which we are less polarized, in which we are less. I think this is
from a compassionate perspective.
Yes, I think that. But of course, no. But from a practical point of view, let's say have a project of 10,000 people. What can you build? Well, I would say try to build a quantum computer. That would be like certainly a completely transformative thing to have. A fully fledged possible building like a quantum computer would finally allow to solve the Schrodinger equation. As I said before, we have the equations, but we cannot really solve them. They are too hard. There's some exponential complexity. Every time you add a particle, the complexity doubles. But with a quantum computer, you would be able to solve these Schrodinger equations in a very natural way, and you would be able probably to solve and create many more new materials, many more drugs that can cure. So what is a huge problem in anything that has to do with chemistry or material science is exactly the fact that we don't understand enough the Schrodinger equation. We cannot solve the equation when you put many particles together, because on a classical computer, the complexity grows exponentially with the system size. Okay, with a quantum computer, that's not the case. A quantum computer is automatically kind of built according to the principles of quantum mechanics, and therefore you would be able to solve these equations. So what you would be able to do with a quantum computer is actually to understand the mechanism of high temperature superconductivity. That's one of these things. There's no reason why it should not be possible to make a superconductor at room temperature. What is holding us back is that we don't understand the physics. We don't understand how to solve the Schrodinger equation with so many electrons that would give rise to this phenomena. There's something, all these particles are very entangled, they are very strongly correlated, and we cannot grasp this. But a quantum computer would be able to do this. So this is why people, especially in the physics community, but I think also in the business community, are so excited about a quantum computer. It would be completely transformative in terms of anything that has to do with chemistry, material science. You would be able to make much better materials and drugs and anything.
Yeah, so that quantum computing bit, and that's where we're talking about the application of this. So it's interesting you lean straight into that. And so to give that some kind of context, I think Google have now tested I think IBM have run some tests, haven't they, with the processing power of these quantum computers. And they've spoken about being able to solve technical challenges and formulas which would take hundreds of thousands of years with a traditional computer in only a few minutes. I think that's, maybe I've amplified that a little bit, but whatever it is, it's absolutely phenomenal transformational impact. For you, that would unlock all of the benefits you've spoken about there. So it would advance science rapidly. It also poses some risks, I believe, because if it can unlock, encryption has been mentioned loads, hasn't it? That actually its ability to then break or bypass any form of encryption. So the risks of that technology could be as profound as some of the other, advances that you've already mentioned of the atomic bomb. They sound as dangerous as they are capable.
Yeah. But maybe if I can go back to the example you gave of this Google quantum computer that was so-called doing something that would take thousands of years or millions of years. These experiments have been debunked. Okay, so actually there are theories. So after these papers were written, people started thinking hard, is it really so hard to do this classically? And actually using techniques that my group developed, we have been able to simulate these experiments in minutes on a classical computer.
Ah, fantastic.
Okay, so these claims about this supremacy, they call it, or quantum supremacy, have to be taken with a big grain of salt. Okay, so we are still very, very far from having a quantum computer that can do useful things.
That's fascinating. Yeah, because I understood that the practical application of this is still a very long way away, but I wasn't aware that had been debunked. That's so interesting. So tell me about that process. So what happened? What it is exactly that Google claim they've done? How did you approach that with a classical computer?
So Google had some system which is actually from the physics or technological point of view is absolutely state of the art, is fantastic. Okay, nobody would have believed 10 years ago that you would be able to do this nowadays. But nevertheless, they have some system of 53 qubits, very noisy qubits, so not good qubits. And they devised a task that basically say, okay, let's do random things with it, something completely uninteresting actually, but that would be hard to simulate with the classical computer. They tried to find, okay, what with the system we can do only a few operations, but what would be hard to simulate on a classical computer? And they did they create some random state, and then they do some measurements and to predict the statistics of the particles, of the statistics of the measurement outcomes. Right. And they predicted, okay, if you do this naively on a computer, it would take millions of years, and we do this here in a few seconds on our quantum computer. But of course, this was without taking into account that the processors or the qubits that they have are very noisy. Okay, that's the big hurdle in building a quantum computer, is that it's very difficult to isolate quantum systems from their environment.
Just explain noisy.
Noisy means that the qubits are not perfect qubits. They're not just zeros and ones. They are also correlated with noise, with photons that fly to the moon, to the sun, or whatever. With things that are from the outside. So when a system is not purely isolated, that it interacts with its environment, this causes decoherence, and this makes that the qubits are not good qubits. They are like the qubits are deteriorated.
Does that mean it's inefficient, or does it mean it's inaccurate, or does it both?
Both.
Okay.
So that there is some kind of a notion that these qubits, if they interact with the environment, and it's very difficult to isolate the quantum system from the environment, then there is some process going on that makes it both inefficient and inaccurate.
Is the inefficiency and inaccuracy to the point where you wouldn't really trust it or qualify it to be a quantum experiment?
We know the equations. We can write down the equations that tell you how the physics goes. No, so it's just that these equations are very hard to solve, but we know exactly how to simulate these equations. And what is going on is that if you wait long enough, the noise is completely overwhelming the whole signal, and there's basically no signal. The only signal that is left is white noise.
Right.
So that means that you can only do something quantum. You can only make use of this quantum coherence for a very short time. That means that you can only do very few operations. And in this, with very few operations, you cannot do something. You cannot entangle the particles very much.
Yes.
And that's why it turns out that you can still simulate this. By taking all these things into account, you can actually come up with some ways of understanding the entanglement structure and model this entanglement structure. And this is something developed this in something that's called tensor networks, and we were able to and also many other groups, they were able to simulate or to predict or get the same predictions as they had, because the qubits are noisy, of course, and this is why all the effort for the moment of the companies that are trying to build quantum computers is to fight that noise. So how do you fight noise? Is by encoding or introducing some redundancy in the system. So what is very interesting actually is that error correction is already happening also on classical computers. So if you would take your cell phone out of the atmosphere to the moon or out of the atmosphere, it would completely stop functioning, because there's lots of gamma rays that would flip the bits that you have in your phone. Like a 0 would become a 1, and then of course it would not function anymore, because there would be errors everywhere. So if you want to take a computer to the space station, you need to make that as some error correction. So how do you do error correction? One bit, you could encode it, for example, in 3 bits. You say, okay, a 1 becomes a 111, a 0 becomes a 000, and if one of these bits is failing, you can still do some majority voting.
From a practical perspective, what's happening there for that phone not to work?
The bits in your memory or in your processor are kind of randomly being flipped.
By the
gamma rays, and with all types of radiation, these are very high energy.
So what happens is, I'm going to put this into practical, and I did say I'm going to keep doing this. It's brilliant, by the way. I'm loving it. It's great. So what you're saying is, as we leave the atmosphere of the Earth, right, the waves that make up our reality change. Is that right?
One of the biggest roles of the atmosphere is to block the very high energetic waves from gamma rays. They are absorbed by the atmosphere, and that's why we are safe here. We don't have to, because they are very high energy. We would immediately get cancer if we would get those, but they are absorbed.
So it's directly related to the radiation and the gamma.
Has to do with but outside of the atmosphere, of course, there's lots of these gamma rays, and these gamma rays, if they kind of enter into a chip, they would flip bits, or in your memory would flip bits, and it would be completely useless.
The reason I dig into that is just to get a practical understanding of the fact that the things that we're building on this planet and the technology we're building is actually then dependent on the atmosphere and environment that we're working on. So that's helpful to understand, I think, from people trying to get a practical understanding of physics, because then they can start to understand there's a relationship between everything.
Indeed.
Yes.
And it turns out for a quantum system, there's lots of rays that are not blocked by the atmosphere. So for quantum systems, there's this plenty of rays and interactions that actually are not blocked and they are continuously flipping these qubits.
Right.
And that's why you need to have a much better type of error correction for quantum systems than for classical systems.
And if I dig into that, what you were saying there before, that error correction, and you're talking about creating this redundancy, so you've got to try and create an environment for where it's protecting the behavior of
these qubits,
those qubits, so that they are not being infected or affected.
Indeed, and it's much harder to do this for something that can be in a superposition than something that's either a 0 or a 1.
Well, it's effectively got more parameters to it, I guess.
Yes, but also it's like a continuum that you have to be able to store or to protect, and that at first sight it looks even impossible.
Right.
But it turns out that it is possible by very smart people. Actually, the biggest genius of the field of quantum computing is called Peter Shor.
Yes.
And Peter Shor did two major things. So first of all, he realized that the quantum computer could do something useful. A quantum computer would be able to factor large numbers.
Right.
Okay, and large numbers, this might seem a very arcane kind of topic, but that is something that on which the safety of the internet is based on. If you can, so whenever you send a message over the internet and it's encrypted, the encryption is safe because it is very, very hard to factor large numbers.
Yep.
But what Peter Shor realized is that with a quantum computer, you can actually factor large numbers very efficiently.
Right.
Okay, and that's, well, one of these bad things of a quantum computer. No, a quantum computer would be able to solve that problem exponentially faster than a classical computer can do.
Yes.
And that shows you the power. Okay, you can actually do things that are very hard classically. But just to make immediately clear, we are still very far from having a quantum computer that can do this.
You mentioned that what makes a quantum computer different is the state of those qubits. That a qubit is effectively matter which has more than just a 1 or a 0 state. Help me just understand that in simple terms again, if you would.
The basic principle of quantum mechanics is the superposition principle.
Yes.
It tells you that particles can be in a superposition of being here and here, or a qubit can both be in a 0 and a 1, and there's infinitely many different ways in which one qubit can be. But if you start looking at two qubits, they can also be in arbitrary superpositions of their two states. So you have a 0, 0, 0, 1, 1, 0, and 1. So you see, this is something that grows exponentially. So the more qubits you have, the more the number of possible superpositions of all these particles becomes like gigantic, it becomes enormous. Okay? And what happens is that by making a computer that is based on the superposition principle, you can parallelize. You have an enormous parallelization. You can basically solve many problems at the same time because you kind of run them in parallel. The difficulty is actually you have all these problems that run in parallel is that at the end all these solutions have to interfere again. These are waves that interfere to give you one solution. And that's actually the very hard part. It's very easy to make an algorithm that solves many problems in parallel. The hard part is to make sure that at the end all these solutions converge again to one thing that you can measure.
Right.
Okay, and there's very few problems for which it's understood how to do this.
Right.
The most important problem that it's understood to do this is actually simulating the Schrodinger equation, because that is exactly the point. This is the Schrodinger equation, and this is what is holding back theoretical physics, is solving this solution. But there's also another class of problems, some problems that have nothing to do with quantum, that you can reformulate in terms of waves. And that was the genius of Peter Shor. He realized that he could rewrite or reformulate the problem of factoring numbers as an equivalent problem that has to do with interference of waves.
So classical computers' processing power is based on 0 and 1s. You can be a 0 or a 1. Look at a quantum computer, you can be a 0 or a 1, or you can be a 0 and a 1. And you can be anything, any combination of those. And what you mentioned there a minute ago is that what that difference creates is the fact that the processing power, it can process and think through things in parallel. That qubit state basically allows it to compute or process way more calculations in parallel at the same time. And is that the basic premise?
That's the basic, like indeed. So classically, how would you factor a number? You would say, look, take a number. Okay, let me guess. Is it divisible by 20? Okay, or you kind of look at it and you look and no, it's not divisible. And what a quantum computer could do is basically it looks at, is it divisible by 1, 2, 3, 4, 5. Of course, it's divisible by 1, but okay. Is it divisible by all possible numbers? You do this in parallel. You can immediately look at, is it divisible by all these numbers? And then, for some magical reason, all these solutions interfere and give you basically a wave pattern. And out of this wave pattern, you deduce what the factors are.
So it can process in parallel and also deduce the answer from the permutations of all of those processes.
Yes. So it's very complicated, and that's Peter Shore's genius to understand all of these steps. He put them all together.
Yes, it's something that, like you say in your book, everyone should start to pay attention and have a little bit of knowledge, and you break it down really wonderfully. And you yourself have, you and your team at Cambridge and what you're doing there, you've started to build out some of your own theories, and I've noticed that there are a number of particularly important points you raise from your lens, what you prioritize, and one of those is symmetry and a couple of others. Do you want to talk us through those?
Let me maybe take a step back and try to explain why we wrote this book. So at some point I received some prize in Belgium, and there was an interview in the last in a journal, and there I said that I didn't understand that people would spend so much time reading a book like War and Peace of Tolstoy, which is extremely complicated because you have to take notes. No, you cannot just, you have to kind of take, this person, that's what they do. Without notes, you are completely lost. And people they find this completely normal. They do this effort. And I didn't understand they would do so much effort for this, but they would not do any effort for understanding even a bigger masterpiece, namely nature. Okay, yes. And that struck a nerve with an editor of a publishing company, and some of the next weeks they contacted me and said, we have to write a book on quantum physics. I said, sure, how difficult can it be? Because I've been working on this for my whole life. Let me do this. And I tried to do this, and for me, it was very clear that what I wanted in this book. I wanted to make the basic principles of quantum mechanics understandable. Like, what are somehow the milestones in quantum physics that are part of our culture, that everybody should at least be aware of. That if you know them, it would make the world much more beautiful, because that's at the end the goal. No, if you know more, then actually it's just the world is much more beautiful. And what I didn't realize is that it would be so hard to write this, and I completely failed. And that is where Celine came into the picture and saved him, and at the end wrote the book. But let me, before we talk about this, let me go quickly through the different milestones of the really kind of important concepts in quantum physics that shape everything we understand in quantum physics.
Absolutely, do it.
So the first thing is that, it's about waves. Okay, that particles can both be a particle and a wave, and that there's no contradiction between classical and quantum there. It has to do with this de Broglie wavelength. Okay, that's parameter that we talked about before. That's something like this: the lighter it is, the larger the wavelength, the heavier it is, the smaller the wavelength. And at some point, if the waves that describe a particle have some extent that is related to this wavelength, and if the particles that are in your system overlap, then this is a purely quantum system. If they don't, that's a classical system. Okay. And there's some kind of a continuous way from going from one to the other one. I think that's a very important concept to at least see that there is some systematic way from going from quantum to classical. It's not one or the other one. No, there's like a very nice, smooth way of going from one to the other one.
I want to just ask you a question on that. When you say that it's either a quantum system or not, everything has a quantum underlying foundational principle to it. So when you say, is it a quantum system or not? What do you mean by system in that?
Okay, maybe indeed I'm using lots of...
That's good.
It's indeed very complicated. So what I mean by this, do I need to understand the laws of quantum mechanics to describe, let's say, the trajectory of that football?
Yes, got you.
I don't.
Yeah.
Okay, because
so it's whether you need a quantum system to describe it or not.
exactly. So
Gotcha.
and this is actually one of the other things. Okay, this will turn out to be one of the foundational insights of quantum physics, that indeed you have these different scales at which different laws come into effect. But I will come to this in a minute. So, but anyway, so you have these waves, but then it turns out that this is not enough to understand the world. Okay, it is not enough to understand why matter exists. Okay, it turns out that these wave functions have lots of symmetry. Okay, that there's something like that is completely exceptional and is purely quantum concept, is that every two electrons in the world are exactly identical. There is no way of distinguishing two electrons from each other. Okay, if this is electron 1, electron 2, this has the same description as if you permute them, it must have the same wave function. I cannot attach an identity to a particle. Particles are completely indistinguishable. Okay? Right. This is a symmetry. So if I have this wave function and I switch these two particles, the wave function of this new system turns out to be the same as the wave function of this old system. But that's not quite true. Turns out that for electrons, there's a minus sign coming in front. There's some kind of a symmetry so there's a hidden symmetry in the description of these many body wave functions. Once you start talking about many particles, suddenly there's some new concept arising, and this is actually something that was formulated by Pauli, and it's called the exclusion principle. And this is the most important force in nature. This exclusion principle that tells you that particles are the same, actually, and if you exchange two particles, the wave function has to get the minus sign. This actually prevents two electrons to be on the same space. Okay, this repels them. This is by far the strongest force in nature, because if you have two particles and you exchange them, and you get to have a minus sign in your wave function, if they would be on the same place, if they have the same, they are identical and they are at the same place, the wave function would equal to minus the wave function. That's not possible. The only number that is equal to minus itself is 0. Right. Okay, so there's some kind of this very strange, and again, this is something that we don't understand, but it's a very strange principle. There's some symmetry underlying all these wave functions that prevents particles to be in the same state. Yep. And that is called the exclusion principle, and that is the strongest force in nature. That is the one that explains, for example, the periodic table. Yes. If you have an atom and you start filling the shells, it's because every new electron has to be in a different state. Yep. This is completely based on that symmetry principle. So symmetry is kind of the thing that underlies everything. Okay, it's about the symmetry. It's about very strange symmetries.
Doesn't that make sense in some respects? So so what you're saying there, I might have got this wrong, but what you're saying is effectively they can be identical, but they can't be the same.
Yes.
They have to have
exactly. That's a very indeed. That's kind of already a bit of a paradox. That's exactly thinking quantum mechanically.
Yes.
Yes.
Yeah.
That's exact.
And what that means is they have to have their own identity effectively, but they can be the same. But they can be identical.
The same property. Yeah, indeed. And if I push my finger on this table and this table pushes me back, this is not an electromagnetic force. This is not a nuclear force. This is only and only the exclusion principle. The electrons in my finger don't want to be in the same state as the electrons in the table.
Help me understand that again. I didn't follow that. I followed the bit before, but tell me that again.
The exclusion principle tells you that the electrons cannot be in the same state.
Yes.
Okay. They cannot be. So if I put my finger on this table and the table pushes back, what happens actually is that the electrons in the table tell me they don't want to be in the same state as the electrons in my finger.
Right.
That's why they repel each other. And that's the strong force. That's the strongest force in nature. Much stronger than anything, because it's based on symmetry. So it's absolute. It's not something that scales with something like the law of gravitation. No, it tells you, no, it cannot be in the same state. And that is what prevents me. And this electron has some wavelength, some kind of a de Broglie wavelength, and everything that is inside this wavelength, they repel each other. They cannot be inside each other. And that is the force. So
that has to be the underlying principle, though, doesn't it? Because otherwise, everything would compound.
That is one of these magical things. Before quantum mechanics, nobody had any clue why we didn't shrink into a P immediately, like the whole world should shrink. And what happens is that there's this exclusion principle of Pauli that explains this. Okay. Nobody knows why, but it is just needed. It is the thing that explains, like, almost everything. So that's a new thing that you need on top
Yes.
of the Schrodinger equation. What happens if
Okay.
you put many particles together?
Yep.
You have this exclusion principle, and that explains chemistry, matter, and so further.
Fantastic.
But then that's still not okay. Then lots of evolutions happen, and people started understanding nuclear physics and material science and so further. But there was still a big, let's say, there was still something missing. Indeed, how do you now continuously go to different scales? Why is the physics of biology so different than the physics in quantum? Is it like, if we understand quantum, does that mean that we understand everything? Okay, there was this, because physics was so successful, people in physics thought that everything can be kind of reduced to the fundamental laws of physics. If we understand the fundamental laws of physics, we would understand everything. Okay, and that is actually something that took lots of years. And it turned out that this reductionism is completely wrong. That there is if you put many particles together, that suddenly new laws can emerge. And this is called emergence.
Right.
At some point, you can have like superconductivity, for example. This is a phenomenon that cannot be explained whatsoever from the fundamental principles of a few electrons. You can only understand if you put many things together, suddenly new possibilities emerge. And that is somehow still an extremely open kind of line of research. What happens at these different scales? Okay, what kind of new emergent phenomenon can happen? And of course, it's something that is very tangible. We understand, like, to understand, let's say, biology, I don't need to understand quantum physics. Of course, everything in biology, every material, every organism consists out of particles that are quantum mechanical. But the laws governing how biological systems evolve are completely separate from the laws of quantum physics. There's some kind of a new organizing principles that emerge at every different length scale. Okay, so you can go to, like, from biology, you can go to economy. It's also like a very big organic system. The laws of economy are very different than the ones of biology. So at every different scale, new laws emerge. And there is some kind of a way of understanding this in terms of physics. It turns out that there is actually an explanation, a mathematical explanation why at different scales new laws can emerge. And that is actually, let's say, also one of these really big insights into physics that happened in the 70s and the 80s, 1970s, 1980s. And now actually the newest kind of the last revolution in physics is this whole idea of the second quantum revolution, in which you can make use of this superposition principle of entanglement to make sensors or computers or clocks that are much, much, much more precise or better or faster than anything else. Yes. That is now kind of the things that happen now. But these are, like, if I would have to say what are the big steps in physics or theoretical physics for the last 100 years, these are like, this is the line of thought.
Good. Without going into the detail, just summarize them for me again. We got 1900, 1905, 1924, 1925. From 1925?
Then you have the exclusion principle, which is actually 1925 also at immediately the same time. And then you have basically all the application, material science, nuclear physics, all these things based on quantum physics together with the exclusion principle. That follows all from that. And then you have to wait a long time, and then till the 70s, 80s, this whole idea of emergence.
Yes.
If you put many particles together, somehow completely new phenomena can exist. Of course, people realize this, but the right mathematical or theoretical formulation of this only happened in the 70s.
Give me a practical understanding of that emergence. Can you try and give me some kind of way to conceive and conceptualize that? Yeah.
So the emergence is that. So, like in the book, the examples that we give is superconductivity. One of the examples that we give is that if you put many particles together and you cool them down, then suddenly the wave functions of these particles become like very, very entangled. All particles start losing their own identity and they start pairing up with other particles. Right. And you get completely new physics. You get kind of new physics that has nothing to do anymore with the Schrodinger equation. So you get some new equations that then start predicting, yes, this system will superconduct, which is absolutely amazing. No? A superconductor is something that transports electrons without any friction. Okay, this is like an emergent phenomenon. That's something that only can happen if you have a very big system. You need many, many, many electrons before you can have this.
So by changing the key foundational elements of the particles, their environment, or at that point in time, it can change their behavior to actually warp or change the rules that we have currently put over physics. and quantum
Indeed,
physics.
and there's new laws that emerge that describe what is going on in that scale.
And you said earlier that you can kind of predict those laws. Is that right?
Yes.
So they're not non-predictable; they are predictable.
Indeed. So in some sense, this is even, from my point of view, this was after the Shrodinger equation the biggest revolution. This is somebody called Kenneth Wilson.
Right.
He called it the renormalization group. So basically, he says it does not really matter what the laws of physics are. If you look at a certain scale, there's only some parts of the equations that matter. Most terms if you would have different equations at the very fundamental level, they would still give exactly the same physics at the scale that you're looking at. So that means that it's completely irrelevant what the fundamental equations are, because you would have these changes. The laws would be different there, but they would not make any difference when you try to describe the physics of these emergent phenomena.
Right.
And that's why actually I think it's also philosophically this is pretty deep. It tells you that we probably will never know the exact equations, because it doesn't matter what they are. There's only, at every scale that we look at, there's only a few possibilities that remain.
Right.
Okay, so, and that's probably why we can do physics at all.
Yes.
Okay, because there are only very few possibilities. Most of the equations that you would write down would anyway give the same thing as what they are. Okay, then, and as a physicist, we say, okay, let's then take the simplest one. And that's why the equations at the end that physicists write down are so simple, because it doesn't really matter what the real equations are, because they would give rise to exactly the same explanations or the same predictions.
So you instinctively think that the likely improvements or the evolution of physics will actually just start to fill gaps within our existing framework, effectively, is what you're saying there.
Indeed. I think this is a misunderstanding of the general public that revolutions in physics kind of mean that everything that was before is kind of wiped off the table. That's not at all what happens.
Yeah.
It's not because Einstein came along that Newtonian mechanics was not there. It's still there. It's just in a limit of very large speeds, you have to make some modifications. But at small speeds, it's still exactly right. Everything is still okay. Also, like classical physics just fits perfectly well into quantum mechanics. You just have to talk about particles that are big. Okay, and if they are big, then effectively the new physics that arises is the classical physics. That's kind of one of these emergent phenomena. Instead of the quantum, you don't need to talk about the waves anymore. There's a much simpler description of what is going on in terms of, let's say, your billiard balls or something like that. You don't need quantum mechanics for this, because you're working at a different scale. Okay, and that's the idea, that all these things actually fit into each other, and everything is so. Whenever so there's nobody that will claim that quantum mechanics is the final theory, but any theory that will come, that will kind of follow it, will have to include it. Okay?
Yes.
Because there's everything that we see is just completely compatible with these principles. You can also measure it, you can do tests, so there's no other way of explaining the world than this with something that resembles quantum mechanics. Okay, so this is it just turns out to be correct, and maybe it's not a final theory, but it will certainly be part of a final theory, or a limit of a final theory.
Just help me understand that when you reference a smaller particle, a bigger particle, what is there?
It's not a bigger particle, a bigger system, or like a football is made of many small particles.
Yeah.
But if you want to describe the trajectory of this big thing as a whole, you don't need to understand the trajectories of the electrons in the particle. So it's more about what do you want to describe? What is the system of interest?
Yes.
Of course, what is going on inside the circle is extremely complicated. There's all these electrons, but this is completely irrelevant if you're interested in whether it is over the line or not.
Yeah, whether it's going. Yes. Right. How often do you dig into these conversations? Is it all the time?
Well, the process of the book, I think it took us 1.5 years.
Wow.
And you have to know that before I started writing about it, I knew nothing about it. That was also quite a confrontation, because the first discussions I had with Frank, I realized, this is so interesting, so amazing, so we are all part of this big system. And I realized, but I know nothing about it. Of course, we all had our classes of physics at school, but that's just this. And I was quite a bit ashamed about the fact that I knew so little about it, but at the same time, it made me very curious. And then, just like you do now, I started asking these questions. And as they say, the actual quote is questioning, or a good question is half an answer.
Yeah, but as physicists, as a scientist, we are extremely sensitive to people that ask good questions. And
Yes, so he
it's
was.
exactly what you do. It's also exactly what Celine did.
Yeah.
Good questions is basically that opens up the thing. No? So somebody, and this is rare. There's not so many people that can ask good questions. I think this is exactly what a good podcast is about. No?
Right.
Somebody, the host, has to ask the right question, and then it's great.
Yes.
And that's exactly what happened. And that's why we decided to write a book together. Celine asked exactly the right questions. Questions that I didn't think about. For me, these are obvious because I've been working on this forever. But then Celine said, no, this is not obvious. Explain me.
Yeah,
And that is the result. That is how the book basically kind of...
Yes, I really forced him to explain all these things in a different way, in more human language, because he's used to explain these things with his colleagues and making huge equations on the blackboard and things. And I find it very fascinating why when I attend their lectures, it's fantastic. But he really had to explain it in different words, in more simpler terms. And I will not say our book is not at all quantum for dummies. Some parts stay quite difficult, but at the end, it's worth the effort to try to understand it. And every time you read it again, you discover something new. And at the end, you will maybe not end up by understand everything, but that's not the objective of the book neither. At least you will have a feeling for it. You will know what it's about. And in the best case, you will also start questioning things. And oh, yes, it's true. Yeah, exactly. My finger is not going through the... And you will understand, why is your shirt blue? Why is your shirt white? There is a reason for it, and that's one of the most beautiful things about children, that they are curious. They ask stupid questions, but it's not stupid question. It's about a young small creature that is discovering the world, and that is how Franks often makes the comparison with the book The Perfume. I don't know if you've read it.
No, I haven't.
By Patrick Suskind. It's a French writer.
No, it's a German.
Yes, it's about a man who discovers that he has this gift of smelling. He smells everything, and after you've read the book, it's as if you suddenly I can smell what you ate yesterday, and it gives this new dimension, and that's what we hope to achieve with the book. That when you read, even if you do not understand everything, you can skip parts if you want to, but that you will just realize there is so much more. Reality is so much more layered, and and it's worth knowing something about it. Of course, we will never force anybody you have to read it, but it's worth to know.
No, it's part of the canon. Basically, as a human interested in the world, you should know something about the laws of physics, no? Because it's a big part of what we are and who we are. And indeed, as you say, where we go to and where we come from. It's very materialistic, but nevertheless, it is actually absolutely beautiful.
But if you take art as an example, you can look at it and look beautiful, but it's far more beautiful if you understand the journey that artist has been on to create it.
Yes.
And so it brings it to life, doesn't it? It's fascinating that what's natural to you. I mean, your passion for this and your commitment to it is incredible. It's like you said, trying to distill that down in a way that you can understand it and try to make it more practical. One thing I think is fascinating, and I wonder whether your role in science and in physics, you mentioned before that every day you do something that you absolutely love, which is just, is the dream. But help us understand what that's like. So, what is an average week like for you? Talk about standing around in front of a board with equations and stuff. What is it actually like? You're the professor of quantum physics for Cambridge, which is fantastic. It's a real accolade in itself, right? But what's that really look like? Help us understand it.
Well, I have to say I'm probably not the typical type of professor, because I'm very chaotic. If I start working, I never really know what I will end up in the day. But I have this blackboard, and that is the center of the universe when I'm in my office and my students are there. So I have a beautiful slate blackboard, and we are discussing. We are basically trying to understand and to push things that we are not. So it's very it's very, very small things. No, you try to understand the formulas. You're kind of trying to change things and understand. So if I would do this and this and this, would that be able to? So we are discussing like half of the day. The other half of the day is filled by doing calculation on the computer, and then the other half of the day, we have many halves of the day, is spent by teaching and administration. But the thing, the part of it that is really fantastic is this completely wide open discussions and trying out many things. 90% of the things that we try don't work at all.
Yes,
but that's what fundamental research is about. No? It's really trying to push the boundaries, trying many things out, and just by luck, you will find one of the paths that you kind of explore. It's turned out to be extremely interesting, and then of course you jump into this, and then there's other doors that open, and that's exactly. If I look back at my journey, that's exactly what happened. You have to be extremely open, and always kind of be happy to learn new things. So basically, this is if you like to learn, being a professor is an absolute dream job. No, you have to. It's basically learning always new things, and you're always surrounded by the smartest people, the smartest kids that are very enthusiastic, that want to have projects, that want to challenge you, and there's not, so people maybe think, oh, there's the professor and the students, there's some hierarchy there. That's not at all true. My students would tell me, oh, you're stupid. This doesn't work. This is what it has to. So the ideal student is somebody that when you start doing a PhD with you, he's a bit, okay, you give him a project and he's, I will never manage to understand this because this is so advanced. But at the end of his project, after like say 3-4 years, the student has to think of the professor that he's, how is it possible that he doesn't understand this? Why is my advisor so retarded in some sense that he doesn't understand what I'm doing? And this is the ideal student because they have been focusing on one very particular small problem and they have to become the world experts in that problem. And that's the only way you can push things. So doing physics is something you would think, oh, this is about the big questions. No. Actually doing physics in practice is about the very, very small, very detailed questions, but going into so much detail that suddenly there's some very fundamental principle that you discover that opens up new doors that turns out to be extremely general. Yes. So it's very unpredictable. Okay, so there's no way there's no kind of clear kind of thing. Oh, today I will do this and this and this. This is completely unpredictable.
Both, even me as an artist, if I can say, and Frank as an artist, we are both very creative, but each in our own way. I play with words, with the music in the words, with the sentences, and he has also to juggle with equations, with numbers, with ideas, and also it's not because you have a PhD student with the highest degrees that he's also creative or original in his proposals. You can have, he can just be moderate, but have very good or ask very good questions and be very creative in the way he's approaching a problem. Yeah. So that is a huge distinction. But that's what I like so much about Frank, that he is also very creative, and we both are, but in a different way. We express it in totally different ways, and that makes it so.
But let me add something in that. Like if we discuss on a blackboard, you would think, oh, we write down formulas. Maybe I said this even, but that's actually not true. What we draw on the blackboard are pictures or images. Okay, so we have like an intuition about things. Yeah. Okay, you think about the way you think about quantum physics or anything else is in terms of pictures and in terms of analogies. And that's what we draw on the blackboard, kind of very vague ideas. Okay. And if somehow they make sense, then only after these make sense, you try to say, oh, can we actually now kind of make this hard? Can we actually write this down in formulas and prove this? But the way you kind of come up with the really big ideas is not by reasoning in terms of math, but in terms of images. Yes. And it turns out, I've talked to many mathematicians also about this. It's exactly the same. It's true for many people, and even the most abstract or most kind of mathematical disciplines. The way people really think about things when they say, I understand this, is because they have a picture about something. Yeah. If you say, I have to multiply two numbers with each other, what do you think about? What is this for you? They immediately see, oh, this is a picture. It's like I have some kind of, if I multiply two numbers, it's the area of some rectangle with this and this. Okay, that's a picture. You immediately see, yes, this makes sense. This is what it means. And this is, of course, a very simple example, but even the very complicated things like the Shrodinger equation, we have some pictures, we have some ideas, we think in terms of, okay, I have like some electrons and I have some geometry and I have some lattice, and that's how you reason and think about things.
So you have to be able to visualize it because you can't see it.
Exactly.
And that was also valid for me, because it is a very abstract science, quantum physics. So that's the reason why I make so much use of metaphors, trying to make it more tangible, to make it more visible, and to make people more, to relate to it, things that they can recognize themselves in. That was the fun part for me of writing this book and trying to search after
but
these
you were
images.
also you were angry at me many times.
Yeah, because for you sometimes you still don't understand it, but it's obvious. I said, no, it is not. For you it is. For me it's not. I really had to do a reset of my thinking, because as you said before, it's very counterintuitive.
Yes.
And I was sometimes very angry. I said, but I still don't understand, until Frank said not at various points, but you have to stop trying to understand it.
Yes.
Sometimes you just have to accept it is what it is.
I wonder whether that's the underlying kind of difference, I think, with a scientist, actually, is that you have to have the ability to accept, to progress.
Yep.
Otherwise, I think maybe people like myself would burn out trying to not being able to recognize the point of which to accept.
Mm-hmm.
No, but even as scientists, we take very bold steps without understanding. We just say, "Oh, let's assume this. Where did we go?" And if this looks interesting, then we try to make hard what we do. And indeed, this is actually problematic for many students. Many students want to understand every single step they are taking, and then they don't make any progress. You need this kind of more engineering attitude. I call this the engineering attitude. An engineer is not interested in this. He just thinks about let me get it to work. And it doesn't matter if I understand it or not, let me get it to work. And that is the right attitude for doing research.
But that happens with innovation, doesn't it? You have to paint a picture of how things could look. And then work back as to whether they're possible. And that's effectively, we do that in business. When we're looking to innovate on a service, well, what if we didn't do that? What if the world looked like this in a year's time? How would we get there? And it's very much what we've done in our AI platform, actually. But what's really interesting is two things I'm going to pick up on there, which is this kind of, you mentioned there, counterintuitive. You've mentioned intuition. And obviously being creative is absolutely incredibly intuitive. But you've mentioned as well that the paradox of quantum physics is that it is often the opposite to intuitive. So how does that work? How does that conundrum kind of... So you're operating intuitively, but often the answers are not intuitive.
Indeed, but that's a nice thing in physics. At the end, there's always a way of checking what you're saying, whether it's right, because there are experiments, there's the reality. You're not just inventing a reality, you're actually trying to understand a material, you're trying to understand a superconductor, you make predictions. So at the end, physics is about making predictions, new predictions, and you can test them. And if they're not true, they have to kind of start over again.
Yes.
Okay, and that's what makes it so objective. What makes it actually real kind of a science, something that is, well, it's that makes it very different than, let's say, art. You cannot be wrong in art. And basically to do something new, you always have to start from scratch. In physics, it's very different. You have to always build on top of all the knowledge that is already there.
It's a relay race, really. Yeah. And that's what we also try to explain in the book. It's really one person working on the work on the insides of the other, questioning and saying, it's really a relay race. And that makes it so, that's how it at the end came about, the whole theory.
Yes. When you talk about it, I've done some research on this previously. I think in the UK there are 20,000 PhDs that graduate annually.
Yeah,
Harps, can you check that?
28,000.
Oh, sorry, 28,000. There you go. Yeah, well, I was close.
No, that's
it was close enough.
That's correct. That's for as physicists, this is exact.
You'd be happy with that. So, 28,000 a year, but we're at this inflection point of AI, with intelligence becoming more abundant to us. Is that starting to impact you as a department and as a scientist and professor?
Yeah, of course. There's lots of people that are very worried that. So I think what is extremely strange is that as a human being is that we have to re-gauge what it means to be creative. You would used to think that being creative is to see connections between things that nobody else sees. Yeah. Of course, this AI can see connections between things that nobody has ever seen. So that is not what creativity is about. Okay, so we have to re-gauge basically what is it that we are good in as human beings. But nevertheless, there is something that is very anti-science in the whole kind of AI world. No? So this is really about black box machines that sees things and makes connections, but there's no understanding whatsoever about anything. Okay, so it's effectively the opposite of what we want to do in physics. It's the opposite of what has been so successful in physics, is seeing lots of data and distilling this into very, very kind of few laws that at the end explain everything. Okay, so this AI, this LLMs and all this, what happens is that they don't give you a model. They just give you data and they kind of can predict things, but that doesn't lead at all to any understanding. And in that sense, we are still waiting for AI to actually kind of to use them in physics. In physics, we want to understand things and based on that understanding, predict new things. That has not happened yet. Okay,
right.
That doesn't mean that it will not happen. And of course, there have already been fantastic discoveries using AI, like the protein folding. Okay, but this is, I would say the protein folding was like a computational problem. It's not that people understand it now. It's not about understanding. It's just about doing it. Okay, yes. Doing it, and I don't think because of the advantages, the huge advances in machine learning that people understand the problem better now. They can just solve it, but it's still a complete black box. Yeah. That's not what physics is about. So I think this is still very far from what AI can do nowadays. Maybe it will get there, but it's not. It seems that physics is still a bit of a different thing. Also, for me, the best news that has happened this year is the fact that the new ChatGPT is not much better than the previous one. Okay, so we use this, of course, to write letters and all this, and you see that it didn't advance too much. Okay, so I have the feeling that might be that we're already reaching some kind of a plateau. It seems that this is something that happens in many other things. So like I remember 20 years ago, people say, oh, okay, like the research in China is like advancing so much faster than in the Western world, and it was true somehow. Of course, the quality of research like 25 years ago in China was much worse than the quality of research being done at the top institutions in the UK or the US, and they catched up very, very quickly. And we are very good as human beings in extrapolating. That means if they catch up, that must mean that they will overtake us. Okay, because we think about curves. We see this curve going up, and it will cross this. That has not happened. Okay, it turns out that they kind of have reached the level that we are in, but now we are kind of just at the same level, and there seems to be the really hard problems are now they are facing it, we are facing it. It's not necessarily that they are better in solving it than we are. And I hope that something like that will also happen with AI. That somehow, of course, there's this huge advance, but it will not take away our jobs. Okay, so they will match. They are using the knowledge that we have made as human beings. No, LLMs have never kind of created any new knowledge. They are just kind of seeing correlations and kind of using what is around there in the internet. Yes. But they have not created something fundamentally new. Okay, and that's, for me, this is still a completely open question. Will this kind of trend that these machines are so much smarter than us, will this ever kind of actually happen? Will they ever do something that goes beyond what we can do?
Has it provided a tool for you to better process or faster process? Because its application in other areas, biology, medicine, and chemistry, there are advancements. It's having a positive impact on that, particularly around drug discovery. Or do you disagree with that?
No, yes. I don't know to what extent there's. So it's very difficult to distinguish the hype from the actual advances in the field. Okay, so there's certainly kind of huge advances, but there also seem to be very big limitations. Okay, so as far as I understand, there's people people thought that it would be very easy to replace, for example, very simple things like drive-ins of the McDonald's. Okay, you would think this is very easy to replace with an AI machine. McDonald's invested hundreds of millions in making such a system. It never worked. Yes. Still doesn't work. Even with somehow all the technology that you have with all the best LLMs of the day, you can still not replace a human being with a machine without the machine making a huge amount of errors. Yeah. Okay, so there is some kind of a big limitation in these systems, and nobody knows where the limitation is. But from my point of view as a physicist, it's complete anti-physics. Okay, this whole AI is about black boxes. It's not about understanding. And maybe for me, this will become interesting if it also can lead to understanding things that I couldn't do before.
Is that how the community feels about it in general, or is that you?
I think it's more me than the community. There's many people that are very actively pursuing research in using LLMs in their research. But I've seen many papers about this, but I've never seen anything really kind of useful yet.
Yes.
Okay, so people are exploring and like trying to, for example, what they were trying to do is also model these wave functions with LLMs, because there's also some exponential scaling there that matches this, but it seems that nobody has really kind of made it. Nobody has managed to get it to work. But I might all be wishful thinking. No, maybe I'm just trying to save my job. Maybe
the romance of it.
Yeah, but I have the feeling that in some sense I'm pretty optimistic that due to these machines, lots of boring jobs will disappear, and there will be more and more other jobs that are more to do with creativity. So I think people with the Industrial Revolution, we talked about the Industrial Revolution before, but had the same feeling that why all these jobs are disappearing, nobody will have a job anymore. That's not what happened. It's just that happened is that there were new jobs created that were much higher quality.
Yes.
And maybe it's something similar will happen with this AI. No, that is basically it will lead to kind of completely new jobs.
Yes,
and that is the hope, at least.
Yes, I'm very hopeful. I have exactly the same vision there. I'm incredibly hopeful for that. And I think when I look at the application of it from a chemistry perspective, for some reason that feels like there's more computational, like you say, basically the kind of the calculating of different variables can be. The speed of that can be increased, and it can just be more efficiently, effectively done. But my question from a kind of scientific perspective is, if the knowledge and capability of the LLMs reaches a PhD level of intelligence, okay, and it's efficient and accurate, as a tool, how does that advance you and your department? Would it or would it not? Because the reason I ask this question, right, I'm really passionate about hoping that AI can really unlock a tremendous amount of pharmaceutical and medical and health related kind of advancements for us. It's my kind of hopefully it's the silver bullet that maybe unlocks a tremendous amount. And there's already
examples where it happened, of course. Yeah.
But I'm interested. You're sat there firsthand, right? You go into your department tomorrow, and all of a sudden, GPT has got PhD level of intelligence, consistent. Yeah, it does what it does today, but it's consistent, efficient, accurate at PhD level of intelligence. Does that change anything for you and your department?
Well, I can only see what do I value in my PhD students and what has worked and what has led to the big breakthroughs. And it's not knowledge, it's creativity.
Yes.
It's trying to understand things and really understand things from like abstract from the point of view of images, in terms of discussion, trying to get an intuition about things. And if you really start understanding things, you can say, oh, but maybe if I do this, that would happen. And I don't see...
But
I don't see the machine doing something like that yet. Okay,
but doesn't it mean? And I might have this wrong, right? So please, push me back into my box here, because I'm trying to really understand it. But I would have thought that it would mean that each one of your PhD students has on tap a PhD level of support to validate his ideas and thinking.
Yep.
And to help evolve his thinking. So the creativity would come from the human, the PhD student, but the ability to formulate or consider more concepts or more permutations to their ideas would be more rapid. Have I got that?
Yeah, but okay, so the thing that I am afraid of is that it becomes too simple. If you never had to do the hard work, you will never really understand what is going on. And that's my feeling with it's so bad that students also in high school use ChatGPT. They never have to do the hard work of writing like a nice report, because they just say, okay. And only if you really have to do it and you have to work very hard, and you have these skills and you really understand how these things work. And in that sense, I don't value that skill too much, that you can use ChatGPT to solve your small problems. No, it's exactly the capability of understanding all aspects of your problems that are necessary to make some advance. But this is very personal. This is because I'm really doing fundamental research. Somebody does applied research is very different. It might be the opposite. There it might be extremely useful. But I'm really talking now about the research that I'm trying to do. For this thing, I have not seen it useful yet. Okay, but so what does it mean, PhD level intelligence? What does that mean? Is it that it knows a lot, or that it's a PhD? So you would think that a PhD, when somebody is doing research, that he's very good in solving problems. But that's actually not what research is about. Research is about asking new questions. It's about asking the right problems. And if you we had it before, if somebody asks the right question, actually this is already half of the solution. And that is something that I've not seen yet, that the machine can do, that it can actually ask exactly the right questions. So you have to come up with the right questions. And that is the hardest part of doing a PhD, to come up with your own problems, to kind of see that there's actually new interesting things that can be done and that you can solve.
But wouldn't that be the relationship between the student or the scientist and the bot? That it'd be the scientist that's asking the questions, but they would just have the ability to process and to consider more. I see. I'm wondering if you've got this team of, effectively on tap, you've got this team of researchers available to you, which can think and can process and consider your ideas and questions more rapidly, with a broader perspective.
Right. But there's this nice quote about the history of mathematics. So the history of mathematics is a progression of ideas that were solved by young people who did not know that what they tried to do was impossible.
Yes. Yes.
Okay. So, and that is, so if the machine tells you it's impossible, you will not do it. Okay. So you need to, somehow, in many ways, ignorance is also a strength.
Unbelievably, yeah.
And that's I think this is some kind of an aspect of this that is not really kind of captured too much by okay. So of course there's lots of things that you can know and do and can be much more efficient using machine learning, but there's also sometimes there are things that you don't want to know.
Yeah.
That because you don't know them, you solve it. You can solve it only because you didn't know what was happening before.
Yeah, so
it's a very difficult. It's very difficult, but indeed, at the end, if you go deep to it, we are also just a machine, and I think that is the thing that I find very confronting. Like, why will people not just make a machine like we are?
Yes.
Okay, so at some point this should be possible.
We'll get there. But that's a really interesting point you've raised there, because if a scientist is asking a machine questions and all they're receiving back is loads of information about what has been done before, there effectively that could blind their route to the real problem, which is an interesting point. And we're in this fascinating time, aren't we, where our neurology as humans is going to change most significantly in this world of AI, where intelligence is going to, and they're already seeing it. I think it was an MIT study just recently. Did you see that?
No. So really our brains are processing in a different way?
Yes, changing the way we're processing information. Big MIT study, because we're thinking completely differently. And
not thinking at all anymore.
Yes. Yeah. And there is some kind of profound, that's kind of seeing that profound. Regular users of this are seeing completely different stimulation of the brain, not in a positive way. So I think you're right, which is that does an abundance of anything can be bad, right? But that abundance of information, does it limit the creativity and the activity of your brain?
Yeah.
actually.
But of course, if this is better understood, then it's easy. No, you just make sure that you could program the machine that it only gives you very limited information. It's not difficult.
It's the next problem to solve.
Exactly.
Yes, fascinating. There is a beauty that exists within the scientific community. You've just touched on it, and I've seen examples of that over the last few years, which is just, I think, it's exemplary of how we should run the planet. And I saw recently there was, I didn't know if you saw it, but there was a piece of meteorite that was mined and it was brought back. Did you see that? It was brought back, and landed in. And anyway, so it gets mined. We land something on an asteroid. We mine the asteroid, get a few grams of asteroid of whatever it is, bring it back, and it lands. And then as it lands, if you just follow that process, it's wonderful to see where, first of all, there's this incredible effort to maintain and guarantee the purity of what's brought back. But then the first thing that happens is that then gets distributed internationally and shared by the scientific community with no biases, just very simple, China gets someone, the UK gets someone, everyone gets it. And you're just like, how have we got that part of the planet so right, where we put humanity and the right objectives first? And it's almost like we could learn so much more.
Yeah, but there's also, I have to say that it's not all beautiful. No? There's also lots of jealousy and all this. So we are just humans, no?
Yes,
I think that.
But don't you think that's look, in what other sectors would do that?
Yeah, that's true. No, but that's because this is the scientific method.
Yes.
No, that's the scientific spirit. We want to understand how the world functions, how things are, and there is only one objective to it. It doesn't matter what other people think. No, there is only one right way of doing it.
I can't think of any other sector that would have done that. They would have been squirreled away. What competitive advantage can we get out of this? And so, I can't help but think that there's some real. And look, the funny thing is if we have problems with AI in the future, then we'll be relying on scientists. So maybe, our future and the civilization will lean far more into the science and be more dependent on science than we've ever been, actually. But no, thank you for taking the time out. Really appreciate it. And absolutely. Get your hands on it. When did it come out exactly?
June.
In June.
Great.
Well, yes, the English translation came out in June. The original book was 2 years ago, exactly 2 years ago.
It became the best-selling physics book ever in Belgium.
Yes.
Come on.
Yeah.
Well done. Congratulations.
Yeah, but if I can add something small, I also saw it as my personal duty to introduce many women scientists in the book. Because when we talk about science, everybody knows, oh yes, Marie Curie. But speaking of symmetries, there is Emmy Noether. Without her, Einstein would have been lost, so to speak. But there are so many brilliant women in science, and they are so unknown, and I found it a pity. So doing my research, I was stumbling upon, but there is she and she and she. And so I really saw it as my duty to put emphasis on them, and also because you see it when you enter a class of physics students or quantum physics students, there are no girls. Yeah. And through the book, I want to show them and warm them towards physics students and show you are as capable as men to do this. There is nothing that would refrain you from choosing this study, but
and there's women that were like, when we talked about symmetries, actually the most important mathematician that worked on symmetries in the 20th century was a woman, and she's called Emmy Noether. You've heard of her, but she's a fantastic. The influence that she has had on mathematics is only growing with time. She's like one of the biggest mathematicians ever, and nobody knows her.
That's crazy, huh? Yeah. That's crazy. And it's important to shine light. I'm not actually a big DEI guy. I believe in that we do need the right people in the right roles to do the job. But 1,000,000% I agree with the fact that we have to give people the confidence to take those steps.
Exactly.
And that's super important. That's so important.
So this book should be a little bit an ambassador for female scientists.
Yeah.
I'm not a scientist, but even though the collaboration between me as an artist and he as a scientist was also so fruitful, and I would also stimulate this, that think more cross-sectorial and inspire each other, because it leads to so many fantastic outcomes.
Well, it's becoming front and center, and I know that when we look at STEM technology courses at graduate level, that there's been a bigger, the number of the adoption of those courses by women and the different people has started to become more diverse. There's been a lot of that, but it's not enough.
Not enough yet.
Yeah, anything that can shine a light and inspire people to go into these fascinating areas, all the better. So good on you.
My small contribution.
Okay, but anyway, it was great, and thank you for the great questions, because I already told you we are very kind of sensitive to this. No, but it is like good questions. Any scientist is very sensitive to getting good questions.
If anyone wants to buy this, where can they get it?
Anywhere.
So it was. We entered Waterstones. It was there in the main bookstores. It should be available online. You can also order it online. Fantastic. But
and how can they get hold? And how can people get hold of you if they want to? Is there a Twitter handle or a?
Oh, we're not so very social media minded.
You don't need to share that if you don't. If that's not important. It's more important for this.
Well, I actually I had a Twitter account with many followers, but I quit last year after it became. I found it from an ethical point of view that it was not.
The echo chamber of that algorithm is just incredibly powerful. The amount of stuff I see. I mean, I clicked on some polar bear thing. I mean,
you only get polar bear.
I'm inundated with bears, just fucking loads of bear stuff. Like I got so many bears, and I'm just like. And the problem, we laugh about it, right? If you look at my YouTube, wherever it is, I'm just like, I'm inundated with like grizzly bears, Kodak bears. I'm just like, but the problem, we laugh and joke, but the people that go down the wrong.
Exactly.
And the problem is that as human beings, we're attracted to, distress and problems, and it's a real problem, isn't it?
Click on quantum physics. Click on the book, the book, and then you will get.
People are now kind of blue sky and all that, but Twitter has become a bit toxic now. It's like
yes.
Yes.
Well, look, thank you for doing it. I really appreciate it.